Hello everyone, welcome back to my channel. In the past few videos, we have discussed how to use the forward difference, the backward difference and the central differences for any kind of first derivative that may appear in a partial or ordinary differential equation. So we have taken a very simple example of application of these differencing techniques in order to numerically evaluate this derivative. But as is the case of a lot of partial differential equations or ODE for the case, not just the first derivative, sometimes even the higher order derivatives appear in these equations. So for example, if you consider the Laplace equation, the Poisson equation, or even in our case the heat conservation or Navier-Stokes equations, in all these cases, apart from the first derivative, there's also a second derivative term that appears in the equation. So the focus of the lecture today is to understand how we can use the central differencing scheme and the forward differencing scheme to evaluate the second derivative term. So just like before, we'll consider a function and we'll try to numerically approximate the second derivative. So without wasting any further time, let's get started. So just like before, we will consider that we have a function f of x and we want to evaluate the second derivative, and in this case we'll consider that this derivative is simply written as d square f over dx square, and we want to evaluate it as at a reference point of x equals to x naught. And just like before, we'll be using the Taylor series expansion about certain number of points, and we'll consider this x naught as the reference, and using this reference and by having a grid of which the spacing could be indicated by delta x or small h, we can write the Taylor series expansion for the neighboring points as follows. So this is an exercise that we have done before. So if we have a point that lies forward in space, we can write for that point in this particular way. So I'll possibly be writing only a few terms, and since it's an infinite series, I'll just be leaving the series as it is. So let's write only until the third derivative, and notice that all these gradients are evaluated at x equals to x naught. We can do the same thing for the other side, that is, if I take this entire equation, make a copy of it, and if I just substitute as this plus h, if I simply substitute this as to be minus h, I hope you would agree that some of these terms will change. The first term that will change is the second term on the right hand side. The third term will remain as it is, whereas the fourth term will also have a negative on it. So now, using these equations, we have earlier derived the first derivative, and we'll probably use the same idea as to how we can eliminate some of the terms and compute the second derivative. It's going to be quite simple exercise, so that is why we started off with the central differencing scheme, where if this is my x naught, and if over here I have x naught plus h, and on this side I have x naught minus h, so that my reference point lies in the center. So that's why the name comes in, and let's see how we can evaluate the second derivative using this scheme. So now if I just consider these equations and I try to understand that I want to evaluate this particular term, so we have to ensure that this term actually stays in the equation. So the very simple idea is that we simply add up these equations. Then on the left hand side I will get f of x naught plus h plus f of x naught minus h. On the right hand side we will get 2 times f of x naught, and not very surprisingly this term gets cancelled out, assuming that we have a uniform grid, and I'll just put a line like this indicating that this term gets cancelled out, and similarly the fourth term gets cancelled out as well. And what we have on the right hand side is 2 times h square over 2 factorial times the second derivative of fx naught. And I hope you would agree that the next term in this series would be 2 times h raised to power 4 divided by 4 factorial into the fourth derivative of the function f at the point x naught, and of course the rest of the terms in the series. And just like before, what we'll do is we'll simply try to do the algebraic manipulation in order to get this term. So the idea is very simple. We take the second derivative on the left hand side and we try to look for what is going to be the rest of the series. So what I'm having on the left hand side in the previous equation is the summation of f of x naught plus h and f of x naught minus h, and this term, when it goes over to the other side, it becomes the negative 2 times f of x naught. And notice that this 2 gets cancelled with this 2 factorial. So what we have in the denominator is simply h square. So essentially we are dividing this equation with h square, and we're keeping this f double prime x naught on one side, which is the term that we are after, and we're taking everything else on the other side. So similarly, what we are interested in, what happens to the term over here, and since it's a positive here, it becomes a negative, and since we are also dividing by h square, so h raised to power 4 becomes h square multiplied by the fourth derivative of the function f, and on the denominator I think we should be having 12, and of course there would be other term which I'm not really concerned about. So this is my final form for evaluating the second derivative using the central differencing scheme, and as usual we'll have one approximate, and the leading term of my truncation, leading term where I would be truncating my infinite series, will determine what is going to be the order of accuracy. So let's look at that. So the first part of this equation, which is this part, this is my approximation to the second derivative, and this is what I am interested in. But at the same time I also need to ensure that if this is my leading term of the truncation error, and if the multiple of this leading term is h square, it implies that this leading term has the truncation error of the order of h square. It implies that this is a second order accurate stencil. So just like before, where we were using the first derivative and the central differencing, and we were able to get the second order accurate estimates, the same thing stays true for the second derivative as well. By simply adding up the equations, we are able to get an estimate of what is going to be the second derivative, and coincidentally it also is second order accurate for the central differencing scheme. I hope that this is not very inconvenient to derive, but let's move on to the forward differencing scheme, and let's try to understand how we can use forward differencing scheme. And the core idea is that if this is my x naught location, I'm only going to use the points that are lying forward in space, such as f of x naught plus h, which is the first neighbor of this x naught, and the second point that could be lying further in space, because as we will see, we cannot just use the x naught plus h. That is only one point to estimate the second derivative. So let's look at that now. So now having done the forward central differencing approximation, so now let's try to see how we can use the forward differencing scheme for the second derivative. So I'll be simply copying the equation that we had written previously. So I'll take this equation as it is, I'll make a copy of it, and I'll paste it here because this is my equation that is going to be true for the forward derivative. And let me just get rid of these red lines. So now what we had done previously for evaluating the first derivative was we had simply taken the first term on the right hand side onto the left hand side, and we had directly evaluated this term as it is. But if we want to evaluate the second derivative and use the same strategy, what we will have on the right hand side will also be this particular term over here. So that's not really an ideal situation. You don't really want to express a derivative in terms of other derivatives. You want to estimate the derivative in terms of the values of the function at different grid points. So on the left hand side, if we have a derivative, whether it's a first, second or third, but on the right hand side we should only have the function f. We should not have, ideally we should not have derivatives, otherwise it's just a meaningless practice. So what we need in such a scenario is we need to consider more points. So if this is my x0, this is my x0 plus h, I need to consider the next neighboring point, which is going to be lying at x0 plus 2h. So if I take the Taylor series expansion about the point x0 in order to get what is going to be x0 plus 2h, so you can think that I'm simply substituting or replacing h by 2h, and what we will get on the right hand side is that the first term will remain as it is, the second term will become twice of h times the first derivative, and similarly we will get 2 times h square over 2 factorial times the second derivative, and similarly we have a cube of 2h divided by 3 factorial times the third derivative, and so on. So now we have gotten two different equations. In both equations we have the first derivative and the second derivative, and I hope that you get the idea now. We have to eliminate the first derivative from these equations. In order to do that, we have to do some algebraic manipulation. So if I say that this is my equation A, this is my equation B, so what I'm going to do now is I'm going to say that we want to evaluate B minus 2 times A. So the idea is that in this equation we have just h times the first derivative, and in the equation B we have 2 times h. So in order to eliminate this term, we have to multiply the top equation, that is equation A, by a factor of 2. And if I do that, what I have on the left hand side is f of x0 plus 2h minus 2 times f of x0 plus h. And note that the first term will be negative of f of x0. Then we have the cancellation because of these two terms, but more importantly what I would have is we would have, I think it's going to be 2h square minus h square over 2 factorial, if I'm not wrong. Please double check this calculation because I haven't done it before preparing for this lecture. And then we will have 8h cube over 3 factorial minus h cube over 3 factorial times the third derivative, and so on. So let me just double check whether the numbers are correct. So we have f of x0 minus 2 times f of x0, that leads to mean negative of x0. This term will get cancelled out, whereas this term is 4 times h square divided by 2 factorial, which is 2 times h square minus h square by 2 factorial, which is this. And the same thing is over here, 8h cube over 3 factorial minus. Alright, it seems to be fine, but in case if there are any errors, please let me know in the comments. So this term over here, this simply becomes 3h square over 4, 3h square over 2, if I'm not wrong. Yeah, I think that's fine. And this term over here, this leading coefficient, becomes 7h cube over 3 factorial, which is nothing but 6. So now the idea is that we can, just like before, we can express the second derivative of x0 as simply I think this becomes 2 over 3. Let me see if that is correct or not. I think I have made a stupid blunder. I didn't multiply these coefficients by 2, so this will not, this coefficient and this coefficient will have a separate 2 as well. So let me just correct for that. So we have minus 2h square over 2 factorial, and similarly we have 2h cube over 3 factorial, and yeah, so these things will change as well. I'm really sorry for that. So we get, I think this is simply h square, and this is simply h cube. Okay, that makes the life much easier. So what we have finally is f of x naught plus 2h plus f of x naught minus twice of f x naught plus h divided, this entire thing is divided by h square, and then we have a negative of h times the third derivative of f naught, and so on. So the basic idea remained the same, that we have to use more number of points if we want to evaluate a higher order derivative. So now after doing the algebraic manipulation despite a stupid blunder, let us look at what is the approximate to the derivative and what is the order of error of the leading term of the truncation error. So what we have as the approximate is this quantity over here, which is my numerical approximate to second derivative using forward differencing scheme. So I'll just write it forward differencing scheme, and what we have as the leading term of my truncation error, it is of the order h, which implies that this is first order accurate, right? So by default, if we use at least 2 points, what you end up getting is that this, using the central differencing scheme, you're still getting approximate, that is second order accurate, whereas using the forward differencing scheme, by using 2 points, you're getting a first order accurate scheme, which is the same story that we had for the first derivative as well. I'm going to be leaving as an exercise for you to evaluate the same derivative using the backward scheme. So if this is my f of x naught, you'll be using f of x naught minus h and f of x naught minus 2h, that is twice the distance of the grid spacing. So in this case, I hope that you'll be able to formulate the same kind of approximate for the second derivative using the backward differencing scheme, and you will also find that the approximate will still be first order accurate. So this is the basic story, but in the next lecture we'll try to see if I want to evaluate the forward differencing scheme of the second derivative, but I want, let's say, a second order accurate method. I want to match for the central differencing scheme. What could be the idea? So this is just by considering only 2 separate points other than the reference, but as we will see later, if we include even more number of points, we can have a higher order accurate approximate for any kind of gradient, and that is something we'll look up into the next lecture. But before that, I would really appreciate your inputs. If there are any questions, if there is any feedback regarding this, that would be really appreciated. So until then, I'll see you in the next lecture. Take care.